Good morning, everyone. Thank you so much for coming today, and I would like to thank everyone for all the valuable suggestions that you've given me during my proposal, and especially Dr. Han and Dr. Pan, who have helped throughout this all the work so far. So today I'll be presenting all the works that I've done as part of my dissertation entitled Game Theoretic and Machine Learning Techniques for Efficient Resource Allocation in Next-Generation Wireless Networks. So this will be the outline of the talk. Firstly, I'll give an introduction, then I'll go through the introduction of next-generation wireless networks. I'll talk about the key motivations of my work, the main contributions, the proposed resource allocation frameworks, the conclusions, and the future research directions. So we all know that with the emergence of the Internet of Things, the number of smart devices that we all use in our day-to-day lives has increased tremendously. So this is the data we have from Cisco, which says that already we have 9 billion of end-to-end connections globally, and by 2022 is projected to increase up to 15 billion of end-to-end connections globally. So this massive growth in the number of machine-to-machine connections has been due to the emergence and the spread of Internet of Things across the globe. So the next generation of wireless networks is being designed and deployed by keeping the requirements of these varieties of IoT devices in mind. So the key objectives of next generation networks are around 10 Gbps of peak data rate, latency as low as 1 milliseconds, and up to 100 times the number of connected devices per unit area as compared to DLT. So the key dimensions of next-generation wireless networks are, as you see here, enhanced mobile broadband, which I already talked about, is an objective peak data rate of 10 Gbps, which would come useful in situations like augmented reality, big data analysis, etc. Ultra-reliable low-latency communication, where the latency is as low as 1 milliseconds, which can be used in self-driving cars, etc. And massive mission-type communications, which requires 100 times the number of current available connections, which can be used in smart grid, home automation, etc. So keeping all of this in mind, as I already mentioned, the key objectives are tremendously high data rates, extremely low latency, and significantly high quality of service. So keeping all of this in mind, my main contributions in my works have been towards these four facets of next-generation wireless networks, which are in network flexibility, low latency, traffic offloading, and spectrum efficiency. And in order to achieve network flexibility, one of the key driving forces of next-generation networks is network virtualization. That will be my first area of contribution. The next is to obtain low latency, we need solutions like fog computing. Then for traffic offloading, we look forward to technologies like heterogeneous networks. And for spectrum efficiency, we would need to achieve spectrum sharing, which is implemented which would be my fourth area of contribution. So moving ahead, the main motivations, as I already mentioned, are the huge diversity in use cases and devices in the Internet of Things, ranging from augmented reality to cloud gaming to the health wearables that we all use to drone delivery, etc. So in order to deal with such a variety of sets of entities and their autonomous objectives, we need to model their interrelationships and their strategic decision making. So we require very powerful mathematical models who can do this, and we look up to two frameworks which have been quite popular in the past few decades, which are game theory and machine learning. So in my works, drawn from the strengths of game theory and machine learning to propose efficient resource allocation frameworks for those four dimensions of next generation networks. So these are the key contributions. I've proposed distributed resource allocation frameworks based on game theory and machine learning for next generation networks, which is firstly in the area of network virtualization. Proposed a matching theory-based distributed resource allocation model by considering both the virtual network slices and the user requirements. In fog computing, where we deal with the large-scale optimization of resource pricing for the operators as well as purchasing for users, along with the optimization of the fog resource allocation. Then in heterogeneous networks, where we look at data transmission routing optimization for a heterogeneous network, while simultaneously optimizing the revenues of the mobile users. And lastly, in spectrum sharing, where we propose an attack detection model for dynamic spectrum sharing to identify the attackers or the malicious users. Excuse me. improve the spectrum usage efficiency. So these are my main areas of contribution in my thesis. So firstly, let's go into the contribution on network virtualization. So wireless network virtualization, the concept is basically that we isolate the physical resources, and we aim to share it among different entities. So because of this abstraction of the network functionality from the existing physical network, there exists great network flexibility, and it gives us more efficiency, and it helps in easier migration when newer technologies come in. So the traditional method is that the resource allocation, which is the spectrum and infrastructure resource allocation, it is separated from the user service management by the service providers. So it basically offers pre-configured off-the-rack packages, service packages to the users. It lacks flexibility for taking care of specific user requirements. We propose a resource allocation framework by considering the three entities of abstraction in virtualization, which are radio spectrum slices, infrastructure slices, and mobile users. So which, instead of separating them, we are actually coupling together the resource allocation part and the user service management part by the service providers. So this is a system model that we are looking at. Generally, in a wireless network virtualization scenario, there is infrastructure which is owned by infrastructure providers. There is a spectrum resource owned by the mobile virtual network operators, and generally the MVNOs create virtual slices from these resources and allocate them to service providers to serve users. So we propose a three-sided matching model by taking into consideration all of these three sets of entities. So basically, the spectrum slices need to be assigned to the infrastructures, and they need to be assigned to the users. So we need a distributed algorithm that considers the localized objectives of these sets of entities. So a potential powerful candidate here is matching theory. So we'll look at the very basic two-sided matching model, and we see how we can apply it to our scenario. So this is the basic two-sided classic matching algorithm. We consider a set of men and a set of women. They have their own preferences on each other. So this is Adam's preference list. So he proposes to his first preference, Geeta. So and Geeta accepts him. Now we look at the second man. So he goes and proposes to his first preference, Irina. Now Carl also has Geeta as his first preference. So in this case, now we look at Geeta's preference list. So Geeta actually prefers the second guy to the first guy. So the first guy ends up a bachelor again. So now we again look at his preference list, and we see if he can be matched to his second preference. Yes. So now we look at the last person, and his first preference is Irina. So he also goes and proposes to his first preference. But here we look at Irina's preference list because there is a tie. So she prefers David to Bob. So David is matched to Irina, and Bob has to go with his second preference, which is Fran. So in this case, we say that we have reached a stable marriage. So in our case, we have three sets of entities. So we need a three-sided version of this. So we look at a three-dimensional stable marriage model. So there are three types of matching agents, which are men, women, and dogs. We look at another variant of this model called the 3DSM cyclic model, where each agent can arrange its preferences of the other type of agent in a cyclic fashion. As in, men prefer women, women rank dogs in their order of preference, and dogs prefer men. So to apply this to our scenario, the three sets of entities would be the spectrum band slices, the physical infrastructure slices, and the users. So in order to know what stability is in a three-sided scenario, we need to know what a blocking triple is. A blocking triple is basically a triple of spectrum, infrastructure, and user who basically want to get matched to each other rather than their currently existing partners. So if you take a matching M, we say that it's a stable matching only if all the entities in the matching are satisfied with their current partners. So to know if a strongly stable matching exists in 3DSM CYC is NP complete. So we look at another variant of 3DSM CYC called three-sided matching with size and cyclic preference. So the only difference here is that each agent is allowed to have multiple number of partners. So even to find out if a stable matching exists, here is NP hard. So we add a few plausible restrictions to this model to be able for it to apply to be applied to our scenario. So this is the algorithm we'll be looking at, which is the restricted three-sided matching with size and cyclic preference. So here the restrictions that we impose on the TMSE model is that the preference lists of the spectrums are derived from a master preference list, and the infrastructures of the third set of entities are indifferent with the first set of entities. So once we decide to go for this algorithm, the first step is creating preference lists for all three sets of entities. So these are the preference lists that we used in our scenario. So the preference list of the spectrums will have the users arranged in a descending order of the offer prices, as in the better package the user takes, the more preferred the user is by the service provider. Now, the preference list of the users have the infrastructures in the descending order of the offered quality of service, as in whichever infrastructure would give me a better data rate, I would prefer that infrastructure. And the reference list of all the infrastructures due to the reasonable restriction that we took consists of all spectrums ranked the same. They form a type. So once we create the preference list, now we can go ahead with the algorithm. So this is a spectrum-oriented RTMSE algorithm that we are proposing, which is just it's a three-sided matching RTMSE algorithm from the focusing on the spectrum perspective. So basically, what we do here is we firstly select a spectrum band, then we choose the best user for this spectrum, and then we go for the best infrastructure for this user. So as I already mentioned, it's a matching from the perspective of the spectrum, and as the algorithm proceeds, it keeps searching for the best triple and keeps adding this triple to the matching, which was empty in the first place. So the RTMSE algorithm is proved to stop and output a stable matching after a finite number of steps, which is determined by the number of spectrum band slices and the lengths of sum of preferences lengths of the users. Now we look at another RTMSE algorithm which we propose, which is from the user perspective. So in this, instead of focusing on the spectrum, we initially choose a user to begin with. Then we select the best infrastructure for this user, and then we choose an arbitrary spectrum for this infrastructure because of the time restriction that we imposed. So this is a matching from the perspective of the user, as I mentioned. Again, like the spectrum-oriented algorithm, this keeps searching for the best triple as the algorithm proceeds and keeps adding the triples to the initially empty matching. So the user-oriented algorithm as well is proved to output a stable matching after a finite number of steps, and the complexity is defined by the number of users and the sum of lengths of preference lists of the infrastructures. So we evaluated the proposed algorithm through MATLAB simulations. This is a radius of the network that we considered. We considered 20 number of spectrum band slices, 5 infrastructure slices, and we varied the number of users to learn what the trend is. So this is a capacity limit of the infrastructure that we considered. This is spectrum band capacity, and this is a minimum sign-out requirement of the users. So here, we can see that the red line represents the spectrum-oriented algorithm, the blue line represents the user-oriented algorithm, and we compare it with a centralized approach, which is the decoupled allocation, where the centralized entity or the MVNO MVNO performs the resource allocation in a decoupled manner. So from the figure on the left-hand side, we can see that the user throughput is improved. Mainly by the spectrum-oriented algorithm that we have proposed. There isn't much difference with the user-oriented algorithm. On the right-hand side, we take a look at the user satisfaction, which is defined as the user obtained user experience data rate upon the user expected data rate. So we can see that the user satisfaction is also improved with the proposed algorithm. Here on the left-hand side, we take a look at the system cost performance, so which is nothing but the user data rate upon the offer prices of the users. So we can see that the system cost performance is enhanced using the spectrum-oriented algorithm. And here we look at the cardinality of the proposed algorithms, where the number of users is varied from 50 to 450. And we see that the proposed algorithms outperform the decoupled and random allocations. Here we compare the algorithm run times, and here we see that the proposed spectrum-oriented algorithm performs better compared to all the other three, compared to the user-oriented as well as the other two benchmark algorithms. This is the first part of the work. So we also applied the three-sided matching in network function virtualization. So I won't go into the details here. The algorithm execution part is similar, but I'll just go over what exactly is the concept that we considered here. So NFV is one of the prime enablers of 5G networks. Again, in NFV, we decouple the network functionalities from the physical network infrastructure. It gives more network flexibility, hence it improves the utilization and minimizes the costs. So this is basically the gist of NFV. There are a set of tracking areas which is nothing but a collection of base stations grouped together for ease of mobility management, etc. So the wireless services or the user services in the tracking areas are disintegrated into a set of virtual network functions, and they are hosted onto different software or virtual machines, etc. that exist on cloud networks. So hence, applying the three-sided matching in this scenario, the three sets of entities that we consider are tracking areas, VNF instances, and cloud networks. So these are the preference lists that we consider. So the preference list of the tracking areas would have the VNF instances in ascending order of the service cost, as in the lesser the service cost, the more the VNF instances preferred. The preference list of the VNF instances would have the cloud networks in the descending order of the quality of service. Like we already considered in the previous virtualization case, the better quality of service I receive, the better preferred the cloud network is. And the preference list of the cloud networks would have a type with all the tracking areas ranked the same. So after the three-sided matching algorithm is implemented, we would have such a scenario where different tracking areas are matched to different VNF instances, and the different colors denote the different cloud networks that they are deployed on. So we move on to the second area of contribution, which is fog computing. So in a traditional data service scenario, the data centers are located really far from the users, and this causes issues where we need services with low latency. And hence, a set of small-scale flexible nodes are deployed closer to the users at the network edge, which are called fog nodes. So when we integrate NFV with fog computing, the only difference is that the resource requirements of the users are basically the resource requirements of the NFVs that serve the users. So in our considered fog computing scenario, we denote the operators by the term data service operators or DSOs. We can name the users as authorized data service subscribers or ADSS. So basically, the DSOs need to allocate resources from the fog nodes to the ADSS to be able to serve them, as per the VNF, as per the requirements of the VNF instances that are serving the ADSS. So the traditional resource management is by the network function virtualization orchestrator, who centrally allocates resources to the users. The proposed method is a distributed allocation, considering the competitions between the DSOs and the ADSs, as well as the allocation from the fog nodes. So this is a system model that we are considering. We consider a set of k DSOs, n number of ADSs, and m number of fog nodes. So the DSOs allocate, so the unit of resource that we are considering is computing resource blocks or CRBs. So the DSOs have to allocate CRBs from fog nodes to the ADSs. So here, competition exists among all the DSOs for providing services to the users. There exists competition between all the ADSs to receive service at a reasonable price and minimize their cost. And also, the DSOs have preferences on fog nodes according to their the cost, resource cost they provide, and they also need to meet the VNF needs of the users. So, taking all of this into account, we will need a distributed algorithm that can meet with all of these requirements. So basically, we need to model the competition between DSOs and ADSs, and we need to allocate the fog node resources to meet the VNF requirements of ADSs. So this is the structure of the algorithm that we are looking at. So in order to obtain resource allocation in a large-scale fog computing scenario, we'll need to model the competition between the operators and the users. For that, we look at a hierarchical optimization scheme. Then, since it's a large-scale scenario, we optimize it using an ADMM. Then, using the values from the ADMM, we perform allocation of fog node resources as per the VNF requirements of the users. In order to do that, we propose a matching-based algorithm, and hence we obtain a distributed resource allocation for fog computing. So as I already mentioned, we go for an EPEC, an equilibrium problem with equilibrium constraints framework to model the competition between the two sets of entities. So they are nothing but hierarchical optimization problems. So as you can see here, the first level in the hierarchy represents the revenue optimization for the DSOs, and the second level in the hierarchy represents the revenue optimization for the ADSs. So here, the decision variables for the sets of entities are the theta ij are the prices offered by the DSOs to the different users, and the Xij are the amount of resources purchased by each ADSs from the different DSOs. So considering those, we perform a hierarchical optimization for the DSOs and the ADSs, and hence we use an EPEC framework. So here, basically, the DSOs provide certain incentives to the ADSs to regulate the competition. Here, we consider incentives as adjustments to the modifications to the resource prices that they've announced. Considering the large number of entities, we need a large-scale framework to solve this EPEC, and hence we invoke an ADMM for this large-scale problem. So ADMM is used for optimization problems of this form, which is applicable in our scenario, and solves it by using an augmented Lagrangian term along with the Lagrangian. So ADMM is very well suited for large-scale scenarios with such optimization problems, and fast convergence is proved to happen for when the objective function is convex. So this is a proposed ADMM for EPEC algorithm in our fog computing scenario. So initially, you can see that the input is theta ij. So initially, the DSOs announce the prices of the resources that they are providing. Using these announced prices, in the inner loop of the algorithm, the ADSs perform revenue optimization to obtain the optimum amount of resources that they need to purchase from the operators. So using those Xij values from the inner loop optimization, the DSOs perform optimization to obtain the optimum amount of prices that they need to give to the ADSs. So as the algorithm keeps on running, and the outer loop terminates when the total profit of the DSOs converges. The ADMM-based EPEC algorithm provides us with the optimal resource prices for the DSOs, as well as the optimal amounts of resources to be purchased by the ADSs from different DSOs. So once we have this, now we need to know how to efficiently allocate resources from the fog nodes to as per these resource requirements. And hence we move on to the second part. The second part involves a matching-based algorithm for allocating the fog node resources. So the values that we obtained from the ADMM for EPEC is the optimal amount of CRBs to be purchased by the ADSs from the different DSOs. Those are basically nothing but the virtual network function resource demands. So and hence we propose a many-to-many matching algorithm for FN resource allocation. So here, the DSOs and the fog nodes have preferences on each other. Basically, the DSOs have preferences on the fog nodes according to their service costs, and the fog nodes have preferences on the different Xij values. In our scenario, we consider that the larger the value of Xij, as in the higher amount of resources it requires, the more preferred that particular VNF instance is. So that's the logic we are using here. So accordingly, the DSOs and fog nodes create their preference list, and we perform a many-to-many matching. We run a many-to-many matching algorithm as per the preferences of both sets of entities, considering the capacity constraints of the fog nodes. So this is the part where the preference lists are created, and this is the part which considers the many-to-many matching between the fog nodes and the resource requirements of the different ADSs. So we evaluated the performance of this algorithm through MATLAB simulations. So we considered 5 DSOs, 20 ADSs, and 25 number of fog nodes. The ADS's workload rate was considered to be Poisson distributed with an average value of 1,000 per second. So on the left-hand side, we take a look at the convergence of the ADMM. We see that the total DSO profit as well as the ADMM error converges within a few number of iterations. On the right-hand side, we take a look at the total ADS's profit and we take a look at its trend when the ADS's arrival rate is changed. So we can see that as the ADS's workload arrival increases from 200 to 5,000, the total ADS's profit also increases. So these are the simulation results for the second many-to-many matching part, where we compared our proposed many-to-many algorithm with a centralized approach, where the NFVU allocates the resources centrally to all the entities involved. So on the left-hand side, we take a look at the total resource cost paid to the fog nodes by the DSOs. So on the first graph, we have varied the number of fog nodes, and on the second graph, we have varied the number of ADSs. So,
one iteration to converge it.
So we've set the error as 10 to the negative 3. Mm-hmm. So to achieve that, it took like four iterations to converge. So if the error value is more, obviously it'll take.
Let's see. No, I meant on the right side, 81 iteration. It's essentially flat after one iteration, right?
Yeah, there is just very minor difference because here.
Did you start very close to the answer or what?
Sorry?
Was your initial condition very close to the answer?
Not really. So the initial theta values that we set were random values between 0 and 1, and then maybe like with more number of entities, it would change.
Typically for ADMM story, it will convert 1 over n, something like that. So basically this one round to go there, a little bit too good to be true.
It looks too good to be true.
Exactly true.
Maybe if we take a look at the individual cases, so even here the DSO profit, you see that there isn't a lot of difference in the.
Exactly. It's like that's why I was wondering, did you start so close to the right answer also?
Yeah, I think left round makes sense. 3, 4 rounds to convert, very typical. But 1 round, maybe because of profit. Okay, the profit is kind of nonlinear or something like that. At beginning, okay, you make a little bit of profit, adjustment, the profit immediately become good. And what is the difference between a billionaire and a trillionaire? Right?
That's possible. Something was checking just to verify that. It looks as I said, a little too good to be true.
And as I mentioned, we look at the total CRP cost paid to the fog nodes by the DSOs. We compare a many-to-many approach with a centralized approach where the NFVO is centrally performing the allocation. We see that the total CRP cost paid to the fog nodes is lesser in the many-to-many approach compared to the centralized approach. We see that when the number of fog nodes and ADSs are not very close together, because in this case we considered the number of ADSs to be 20. So when they are close together, the cost difference isn't much. But when the number of entities, the difference between the number of entities increases, the cost difference is more. In this case, instead of the number of fog nodes, we varied the number of ADSs. The number of fog nodes was fixed at 25. So here again, we see that the cost difference increases as the number of entities increase. On the right-hand side, we compare the algorithm run times between the many-to-many matching and centralized. But here we can see that there isn't much difference between the centralized and the proposed approach, which is understandable because it's the many-to-many is a distributed approach where we have to look at preference lists, etc. So we also see that as the number of entities, the number of ADSs increases, the difference is further increasing for the algorithm runtime. So the third area of contribution is heterogeneous networks. So due to the current radio frequency spectrum crunch that we have, harnessing other sources of bandwidth is inevitable. So with around 300 terahertz of bandwidth, visible light is a very promising candidate. But visible, even though it has advantages like the LED sources, which are VLC sources, are ubiquitous, it has restrictions like there is only limited coverage because it cannot work in strong sunlight or shaded areas, etc. So if we can combine it with a technology which can offer improve the coverage, that would be good. So we combine it with a device-to-device communication technology where the mobile devices can transmit data directly between each other rather than transmitting it through a base station. So we consider a VLC and D2D heterogeneous network in order to improve both capacity as well as coverage. So again, for such a scenario, in order to find the data transmission routes from the transmitter to the end mobile device, The traditional approach is a centralized calculation by the VLC service provider, which centrally calculates the routes based on minimum path delays to the end mobile device. But the proposed method is a distributed method considering the device-to-device revenue optimization as well. So this is a system model that we are considering. We consider k number of VLC transmitters belonging to a VLC service provider. We consider a set of mobile devices which are sitting directly under the VLC transmitter, and they are called the mobile users in coverage, MUICs. And we consider a set of mobile devices which are which are away from the light of the VLC transmitters, which are called MUIDs, or mobile users in darkness. So this communication is through VLC, and the communication between the mobile devices is through UTD. So such a data transmission environment is a highly dynamic, considering the two sets of communication technologies involved. So we need a centralized solution which is feasible for the VLC service provider as well as the mobile devices is difficult. So we need an optimal distributed routing for such a dynamic environment. This by a data transmission route, this is what we are considering, a transmission route for a data packet from, say, VLC transmitter 1 to through the next mobile devices to the MUID, which is shown in red here. So we need to find an LHOP, a data transmission route, which is optimal from the transmitter to the end mobile device. So by L, I mean the number of hops. In this case, it's 1, 2, and 3. L is equal to 3. So for such a dynamic and unpredictable environment, in the recent past, machine learning algorithms have been quite popular. Reinforcement learning is an algorithm which helps learn behavior in a dynamic environment, but it helps to learn the optimal policy through trial and error interactions with the environment. So we propose an RL-based route determination, optimal route determination in our considered VLC D2D scenario. And it is a distributed method based on the local, the preferences of the local set of entities here. And in reinforcement learning, Q-learning is a very popular and direct reinforcement learning method, which we employ in this scenario to find optimal data transmission routes. So this is basically the gist of Q-learning. Basically, there will be a reward matrix. So a reward is nothing but a payoff or the utility obtained by moving from one particular state, taking an action from one particular state. So as you can see on the left hand side, say if I'm at state 1, and if I take the action of state 5, I get a reward of plus 100, and hence it is more desirable. So using the reward values, using the reward matrix in Q-learning, this is the Q-learning algorithm where it considers the reward values for a particular state in action, and it considers a gamma factor, which is nothing but it's called the discount factor, which gives more emphasis on the future rewards of the path. So using the Q-learning, using this equation, the Q-learning algorithm computes a Q-learning matrix, which would give us optimal policies for a dynamic environment. So in our scenario, the learning agent is considered as the transmitted data from a VLC transmitter to the end mobile device. The state is called the current position of the transmitted data, as in if the data is at VLC transmitter 1, the state is transmitter 1. The action.
There are lots of data simultaneously in the system.
In this, we've considered only one packet at a time. Basically, a single agent reinforcement. So the action.
No, I don't mean the agent, the state. You could have one agent, but you could have lots of
we have considered just one.
packet.
The action is the transmission direction of the agent, as in from VLC transmitter 1. If I should take the action of going to MUIC 1, so that would be the action. The reward is a payoff obtained by performing a particular action from a state, and for our scenario, let's see how that is computed. So considering this is the RL-based route selection algorithm that we propose. So we propose a reinforcement learning-based route determination approach, and for that, the most important thing that we need is reward values. So in order to compute the reward values, we look at two cases. As in, if the current state of the data is a VLC transmitter, we obtain the reward values using algorithm 2, which we'll take a look at next. If the current state is not a VLC transmitter, as in if the current state is a mobile device, we compute the rewards using the next algorithm 3 and update the reward values. So as we saw here, when the current state is not a VLC transmitter, as in when the current state is a mobile device, we model the competition between the mobile devices which relay the data. And in order to, we consider the revenue optimization of the mobile devices which relay the data. So considering that there will be one mobile device which is relaying the data and one device receiving the data, we model it using a two-level optimization. So for that, again, we take a look at EPEC, and for the large-scale scenario, we solve it using ADMM. And using that, we obtain the reward values for the RL when the current state is a mobile device instead of a VLC transmitter. So now we take a look at algorithm 2 and algorithm 3 for computing the rewards. So the first is to compute rewards for the RL scenario when the current state is a VLC transmitter. So there, the reward is simply the capacity of transmission between the transmitter and the first mobile device in coverage. So in the second case, when the current state is a mobile device, we compute rewards for RL using the ADMM for EPEC algorithm, which I have discussed for the for computing scenario. So here, the inner loop consists of the optimization for the current mu-R node, and the outer loop consists of the revenue optimization for the next mu-R nodes. And basically here, the optimal values that we are looking at is the amount of spectrum that the next node allocates to the current node to transmit the packet. So after we run the ADMM for EPEC algorithm, we obtain the optimal values of optimal spectrum values, using which we calculate the data rate for that D2D transmission, and they form the reward in the R matrix when the current state is a mobile device.
That's good. Quick question. So you can compute these once and for all, right? In other words, because the state is the location of the packet,
Right.
Can you do this in advance?
Not really, because only when the data is at a VLC transmitter 1, we see that the next possible states are, say, MUIC1 and MUIC2. And if we randomly choose MUIC1 when creating the Q-learning approach, MUIC1 now will have an ADMM for EPEC between its next set of mu-Rs. So the price of the spectrum and the spectrum values allocated between them might change. Like the revenue optimization between them might change.
So what I'm going to understand is, suppose, I have this network and package is in location or something, that's its state. Now I run this algorithm versus I run the algorithm, say 10 minutes later. Is there a difference in the reward?
Yes. So
why is there a difference?
So for a mobile device which is sitting under the like for an MUIC to its possible MUIDs, say even if the position of the devices don't change, if the position changes, there'll be
Sure.
So if
nothing changes.
if there is no change in positions, they can even the rate of so here we consider that the next mobile devices provide spectrum to the current devices to transmit the data. So the price values of the spectrum which is allocated might change, and accordingly we consider it different in.
Basically, is there some randomness is what I'm trying to ask.
Yes. So between the mu-Rs, so the price at which the next mu-R is providing the spectrum might change. Accordingly, the allocated spectrum might also change.
So
of that,
essentially, therefore, the reward is essentially random.
Yeah, because of that, the output of the ADMM for EPEC would change every time.
I see. The other one is pretty much deterministic, right?
Yes, yeah. The other one is just a VLC transmission data.
I see. Cool. Thank you.
We evaluate the performance of the proposed algorithm through MATLAB simulations. We consider an indoor scenario, the visible light spectrum, and the power is considered that of a white LED. The user power is considered as 300 milliwatts. In this case, we have set the maximum number of hops to 3, as in from a transmitter, it goes to a MUIC1 to a relay to the end mobile device. So the maximum number of reinforcement learning steps is varied from 1 to 100 to study the trend, and the discount factor is also varied to see how the performance changes with more emphasis on future reward. So on the left hand side, we can see that we take a look at 2 cases where there is just 1 transmitter and 5 mobile devices, and where there are 2 transmitters and 10 mobile devices. Since it's an indoor scenario, we didn't consider a very large number of devices. So on the left hand side, we see that the average D2D data rate is increased with the increase in number of learning steps. And on the right-hand side, we see that average D2D delay is decreased with increase in number of learning steps. Here we compare our proposed reinforcement learning approach against a centralized approach where one central entity can determine the optimal routes based on delay. So here we see that the average D2D data rate increases with increase in discount factor, as in the more emphasis is given to future rewards, the D2D data rate is improved and the D2D delay is decreased with.
How many runs is this? One?
This one is.
The error bars. Last week we were both at this PI meeting, and listen, we engineers tend to be very bad scientists. We don't put any error bars. So if you have done multiple rounds, you should put error bars.
Sure. So no change in the centralized route calculation by the VLC service provider, and we have obtained a better performance with more emphasis on the future rewards. So the fourth area of contribution is in spectrum sharing. For that we understand what a cognitive radio network is. A cognitive radio network is an intelligent network which allows the configuration of parameters dynamically, like the transmission protocol, the frequency band, etc. So a cognitive radio network allows to implement dynamic spectrum access for efficient use of the spectrum. So dynamic spectrum access is the technology by which there will be primary or licensed users of the spectrum, and when such users are not using the spectrum, a set of secondary users can sense the spectrum and use it for their communication. So the key decorum in such a cognitive radio network is that the bands are vacated by the secondary users when they sense the presence of primary users. So this is exploited by a set of malicious users called primary user emulation attackers. Basically what they try to do is they take advantage of this decorum that exists in CRN, that they emulate the signals of the primary users and mislead the secondary users into thinking that, oh, it is actually the primary users that are transmitting, and hence they cause the secondary users to lose their spectrum opportunities. So if we can detect PUE attacks for a cognitive radio network, we can ensure efficient spectrum utilization. So the spectrum efficiency can be improved. So this is a system model that we are considering. We basically have a primary network and a cognitive radio network. So the primary base station communicates with the primary users through the licensed bands F1 to F5. So here we see that at the moment F1, F3 and F4 are only occupied. So ideally the cognitive base station should be able to sense F2 and F5 and allocate those bands to the secondary users for communication. But there are attackers who are emulating the signals of the primary users in bands F2 and F5, thus causing the secondary users to lose their spectrum opportunities. So this can be considered as a two-player zero-sum game between the primary user emulation attackers and the secondary users. The spectrum gain for the attackers is a spectrum opportunity loss for the secondary users and vice versa. So it's a two-player zero-sum game between the attackers and the secondary users. So the Nash equilibrium solution here is a minimax solution. So we consider the maximum payoff for the secondary users given the attacker strategy as U, and the maximum payoff for the attacker given the secondary user strategy is minus U. So in order to maximize U and let secondary users win, we need to successfully detect the PUE attacks. So the framework that we propose here is based on the cyclostationarity features of a signal. So cyclostationary features are features which repeat periodically over time. So we observe the signals for a certain amount of time, and we compute the spectral correlation function of the signal, which describes the cross-spectral density of all frequency-shifted versions using this. So from the spectral correlation function, we obtain the spectral coherence, which is the normalized form of SEF. And from SE, we obtain what is called the cyclic domain profile, which is basically the maximum spectral coherence value for each frequency shifted version. So our attack detection is mainly based on the cyclic domain profile values. So we assume that the signal features, the intrinsic signal features of only the primary users are known, and that of the PUE attackers are different from those of the primary users. And we try to detect the attackers based on these different signal features. So for that, a very promising candidate for feature-based classification is deep learning. And of the deep learning frameworks, so in scenarios like this, there is only very limited data for training, etc. So potential network for such a scenario is a generative network like GAN, the generative adversarial network. So a GAN is basically a deep learning framework where there are two networks competing against each other. One is the generator, where it generates values from random noise, and it tries to trick the discriminator by generating hard to discriminate samples. And the discriminator's job is to try and discriminate between samples from whether it's from the generated data or from the actual data. So even though GAN is a very powerful model, there are a lot of issues involved with implementing a GAN framework due to it. It's very sensitive to the hyperparameter selections. It's very hard for it to train and to get it to converge. So in this, we've considered a better trainable version of GAN called the Wasserstein GAN. So considering that, this is our proposed Wasserstein GAN architecture for attack detection. So here we have considered convolutional neural networks as the deep learning networks for the generator and the discriminator. So here, as I already showed in algorithm 1, we obtained the cyclic domain profile values of the observed signals. So we obtained those values from algorithm 1. So as you can see, we observe the signals which contain the PU signals as well as the attacker signals. We compute the cyclostationary features using algorithm 1, and we give it to the GAN framework for classification. So this is a GAN training, Wasserstein GAN training algorithm. This is the training part of the discriminator of the GAN. This is the training part of the generator. So here we use, as the optimizer, we use the RMS prop optimizer, which divides the learning rate by a running average of the recent gradients. So considering the cyclostationary algorithm as well as the Wasserstein GAN training algorithm, we propose our algorithm for attack detection as this. So initially we perform energy detection to locate the user frequency. Then we perform computation of cyclostationary features to obtain the CDP values. Then we input the CDP values into the GAN framework for classification, and which classifies the observed signals as of that of PUs or PUE attackers. So these are the simulation results. So the algorithm 1 to create the CDP plots, that has been run in MATLAB. And the algorithm for the GAN training and testing has been run in Python with TensorFlow as backend. So these are the loss values for the training dataset, which consisted of 22,000 samples. And we considered 256 features, and that was the batch size. We ran it for 70 epochs. So these are the hyperparameters given as standard in the Wasserstein GAN proposed paper. So we implemented using the standard values. So here we can see that the losses of the generator and the discriminator networks are converging, and that the training has been effective. Here we look at the losses of the testing data set, which consisted of 2,000 samples, and we again ran it for 70 epochs. We set the hyperparameters to the standard values of the WGAN, and we again see here that the discriminator and generator losses are converging, and that the classification has been effective. So these are the conclusions of.
Confused. Can you go back to your GAN picture? So, traditionally, the idea is that you're going to put in some statistical source of info there. And once trained, your GAN is supposed to produce something which is indistinguishable from that statistical source.
Yes.
Now you're using your GAN in a slightly different manner, which I'm not quite understanding. So you've got, kind of real data or whatever, attacker data and non-attacker data in there. You train this whole thing. What is your GAN supposed to produce?
So basically, we're using the discriminator of the GAN for classification, whether it's a attacker or not.
Then what's the purpose of the generator?
So the generator is provides, it's a generator framework. It because we have only like very few samples. It's a generator model which enhances the data set by producing data values which are close to the actual data.
So then would it be correct to say that you have to train the system with only one, either generator, either attacker or whatever, the real things, so that you can, I mean, if the goal of the generator is to produce a particular type of statistical information, you should train it with that statistical information, not with both. See what I mean?
Right.
Otherwise, you'll get noise of it, or you'll get some combination. I'm not, what I don't understand is what this output is going to be. I mean, just think of this GAN whole setup as a black box for generating data, right? It is supposed to generate data of the same statistical quality of what you put in, right?
So that is just the generator part actually, which
This is the whole lot. Once you train it, the feedback loop here is to ensure that basically the output is indistinguishable from the training data statistically. But the problem here is your input is both sorts.
right.
So
those
the
of,
output, if your GAN is well trained, would contain some weird mix of both I don't know, both attacker data and real data. I mean, think about it this way. So like GANs typically can be used, for example, to generate cats, right? I train it with cats, the output is going to be cats, right? I train it with dogs, I will get output dogs, images maybe. And it's feasible to do that. If I train it with both cats and dogs, the output, I don't know what it will be. It might be some strange combination of cats and dogs. So that's what I'm trying to say. Yeah, go ahead.
Yeah, but the generator is just helping for the data augmentation part to generate basically more samples, and here we are using the discriminator as discriminating between.
That's the point. Eventually, in a trained GAN, the generator is supposed to be generating something which is indistinguishable from the original data, and your discriminator is supposed to say that, hey, I'm not able to tell the difference. So that's what I meant by cats and dogs. So I send in a whole sequence of cats in there. The generator gets trained by means of that. So the input of the generator is noise, the output is an image, which the discriminator is unable to tell if it's not a cat, and therefore you have succeeded. You see what it's not clear what is going on here is what I'm trying to say. That if your goal is to augment your sample set, you probably then, if you don't have enough samples, for example, then you should train two GANs, one with the real the thing and one with the fake. And now you've got GAN 1 which is generating real stuff, GAN 2 which is generating fake stuff. So now you've got a rich data set potentially, and then presumably you can use some other classifier to tell the difference between the two. But as such, if you're getting nice answers with this, it probably means your GAN is not trained enough.
Also, one thing was it was very, like I tried a lot with the regular GAN. It was very hard for it to train and convert. So that's why we implemented a Wasserstein GAN. So I still have to add a there isn't as such a defined accuracy thing for GAN yet. So need to add some like inception distance or something of that sort to just show how accurate it is.
But you see what the point is.
I know. Yeah, one of my other students, Xun Sheng, doing this, using this one to generate this, because we have Sharon project, they have this kind of graph for UAV to see the graph, but they have a very few graph, so very few sample, and they use a GAN to generate a fake graph, and then he showed me, 8 pictures to ask me which one is real. I cannot tell. So basically here, and at the end you need to, beyond the convergence, previously he just got his code converged maybe last week.
2 days before the
but beyond the convergence, you also need to consider the suggestion that the result should be right. Otherwise, here the generator is generating some kind of fake money for the police to catch, and then you continue to generate this monopoly money, so it doesn't run.
Yeah, so you need to decompose that to 2 steps.
Exactly,
like
that's a good option.
the psychiatrist suggested, right? First of all, if you don't have a rich data set, you generate with the real signal, then you have a real signal, rich data set, then you do the GAN for the fake signal, you have a very rich fake signal data set, then you build up whatever classifier you use. It's not necessary to be
It may not be the same.
Yeah, whatever classifier you can classify, real
and
signal.
also like I told you, because of the time thing, so I'm yet to include not really an accuracy per se, but there are metrics like inception distance, etc. to show the accuracy, so I'm yet to add on to.
I think that, right after this one, write down the comment and maybe send back
Sure.
And you know that the commencement is due December 13th.
Right.
You still have a month.
Yeah,
Sure.
no, it's something to keep in mind.
Sure.
Yeah.
So these are the conclusions of my works. So in network virtualization, the existing framework, like I already mentioned, is a decoupled scenario where the spectrum and infrastructure resource allocation by the MVNOs is separated from the service provider allocation to the users. So we proposed a three-sided matching framework considering the infrastructure slices, spectrum slices, and the users. We saw that there is more flexibility to user requirements due to the three-sided model. That we achieved a better throughput and more number of users were served due to the proposed approach. In fog computing, the existing scenarios that there exists competition. Generally, the DSOs announce their prices, the ADSs purchase resources from them, and the DSOs also have to allocate resources from the fog nodes, which is centrally done by the NFVOs. The proposed approach is a framework where we consider the hierarchical competition between the DSOs and the ADSs. We also proposed a many-to-many approach where the resources from the fog nodes are allocated to the ADSs as per their resource requirements. We saw that the revenue has been optimized for both DSOs and ADSs using the ADM for EPEC framework, and the lower resource costs to pay to fog nodes has been achieved. For a heterogeneous network, the existing framework is a central VLC service provider calculation from the transmitter to the end mobile device. We proposed a reinforcement learning approach, which also consisted of an ADM for EPEC approach to perform a revenue optimization for the D2D users involved. And so we saw that we achieved higher average data rate and lower D2D delay. In spectrum sharing, the existing approach is there exists cyclostationarity-based classification approaches, but for feature-based classification, deep learning is a very potential tool. So we employed a cyclostationary-based GAN classifier to remove the PUE attackers. So we perform data augmentation for limited samples and better attack detection during single feature learning by GAN. The future research directions that I propose is that considering V2X, etc., we can consider the aspect of user mobility in wireless network virtualization. So in that case, we'll have to update the preference list, especially that of the users, more frequently. So right now, the preference list of users consists of the infrastructures in the descending order of the offered quality of service. So that will have to be updated quite frequently when we consider V2X, etc. into it. So we can either, considering, I ran the RTMSC algorithm in my personal laptop, which took a few milliseconds, but running it in a very good processor shouldn't take long. So either execute it repeatedly, or we can add algorithms like the Rothband beta algorithm along with it. So the RBB algorithm basically has a sequence of matchings where each next matching is created from the previous matching by just satisfying a blocking pair. So it's more dynamic in that sense. Maybe by adding such algorithms to the RTMSC approach, we can improve it for user mobility. And in IoT fog computing, as I already mentioned, the requirements are like diverse, very diverse. So right now we have considered only that the fog nodes consider the VNF resource requirements in their descending order, as in the higher, the larger the amount of resources required, the more the more priority given to that VNF instance. But if we can study the demand patterns of VNF instances as per different use cases, maybe we can tailor it more to different use cases and make sure that the CRP cost is further reduced. These are my publications so far, the transactions publications and conference publications.
Okay, thanks for the speaker. The light.